Good morning, good afternoon, or good evening, depending on what time of day you're looking at this video. My name is Steve Nightingale, and I'm going to be running a project this year entitled UK Net Zero Strategy, Balancing the Energy Demand. The problem that's given rise to this project is the fact that the burning of fossil fuels produces gases in the Earth's atmosphere which trap the sun's heat. This is known as the greenhouse effect. This process makes the Earth warmer and causes significant changes in weather patterns, and we've all seen and heard about many of these over recent years. The reaction to this problem by the UK government was that in July 2018 they launched their Road to Zero strategy, where the plan was that the UK would reach net zero emissions by 2050. One of its ambitions in the short term was that at least 50% and as many as 70% of new car sales and up to 40% of new van sales would be ultra-low emission by 2030. That's in less than 8 years. Most recently, in October last year, they published two further documents, the Net Zero Strategy and the Heat and Buildings Strategy. And they set out how the UK will deliver on its commitment to reach net zero emissions or be completely green by 2050. The result of this strategy is that there will be increased use of acceptable green renewable energy systems to produce electricity, for example, wind and solar energy farms. However, the intermittency of these technologies and other sources of electricity produces a very strong demand for efficient, cost-effective, high-capacity energy storage and distribution systems. And this in turn produces an increasing requirement for rapid charge and discharge cycles of energy storage systems. For example, ultra-fast charging for road transport at service stations. At the moment, we have a very small percentage of electric vehicles on the roads. And in the future, we're going to have a much larger percentage. And with the recent improvements in battery technology, we'll find that we can charge at a much faster rate than previously. And the high currents required by this cannot be met by the existing grid infrastructure. One will need to have some kind of buffer or local energy storage in order to cope with this. And one obvious solution is to consider using a chemical battery. So this would be effectively trickle charged over 24 hours, but could take the load of a very high current requirement for a short period of time for the rapid charging of the batteries in cars and vans. So the project is to identify and select the optimum approaches for generating, storing and distributing electricity, both on a small and a large scale, and determine how these can be best applied to achieve the UK government's targets. In common with all MDDPs, there is also a financial aspect to it, and this is to determine the cost of implementing the approaches that you have selected. Here is a photo of a wind farm. I'm sure you've all seen those throughout the country. And essentially we have onshore and offshore types. The offshore ones have the advantage that the wind blows more consistently and you get much better efficiency. But this is at the disadvantage that they cost more to maintain because you have to access them via a special ship. And you also get higher maintenance issues due to the salty environment. Here is a photograph of a typical solar energy farm. Again, you will have seen these solar cells in many places throughout the country, either in fields or on top of buildings. And the efficiency of solar cells has improved from about 8% 25 years ago or so to something in the early 20s these days, as well as the production costs having decreased. However, one of the problems with using both of these technologies is the intermittency of the source. In other words, the wind doesn't blow optimally all the time and the sun doesn't shine optimally all the time. And this means that you can't run at installed capacity all the time. Now, if you look at the information the government's put out, it's shown that we could generate up to half our electricity requirements from renewable energy sources, but this is rather deceptive. Firstly, because of the intermittency of the energy source, and secondly, because you can't store a lot of the energy because we either don't have the facility to make use of all the energy because of what's coming from conventional generating stations, or we don't have any storage system. So in practice, what happens is the net contribution that you get from this 48% of installed capacity is considerably lower. Typically, a wind farm or wind farms overall contribute about 25% of their installed capacity, and solar energy farms about 17%, with the result that the 48% of installed capacity seen on much government literature is actually decreased to less than 10%. Now, this can be improved by having some sort of storage system, and this is one of the things I want you to look at. Something else one should consider is there has been quite a lot of discussion about moving towards a hydrogen economy, and it's been broadly stated that cars won't be running off batteries in the future, they'll be running off fuel cells powered by hydrogen. Well, this is rather simplistic, and there's strongly divided opinion by car manufacturers on whether that will be the case. What seems to be coming to the fore is that probably batteries will continue for domestic vehicles, maybe fuel cells for larger trucks and vehicles that are going longer distances. However, if we are going to use fuel cells at all based on hydrogen, we could look to store the energy from a wind farm, not just in a battery, but actually use it directly to convert water into hydrogen and oxygen using an electrolyzer. And there are several types of electrolyzer. I've listed three here: the alkaline, the proton exchange membrane, and the solid oxide electrolyzer. And the hydrogen produced by these could be stored for later use, or it could be fed directly into a gas distribution infrastructure, possibly replacing the current one used for natural gas. And if one looks at the issues in doing that, you find the problems are not too dissimilar in terms of what it's going to cost from when we switched from coal gas to natural gas. And so we could switch from natural gas to hydrogen with a similar sort of expenditure. There would be some other things that need to be considered as well. And this in turn would mean that instead of the current government plan, which is for all new properties, flats and houses built after 2025, to be using heat pumps, not gas heating boilers, one could look to continue to use heating boilers, but they would just be powered by hydrogen, not by natural gas. Now, many of you will have heard of the fact that the company Tesla, which is one of the major manufacturers of electric vehicles, has used its lithium-ion battery storage technology to make a 150 megawatt storage plant in Australia. And they've also done this in other countries. And this, to my mind, is a kind of hero experiment whereby they've taken existing technology that's mature and used in vehicles and shown what could be used to store electricity. However, it's not the optimum way of doing this, because the reason we use lithium-ion batteries in cars, or one of the main reasons, is because it's a technology that works at ambient temperature and it's pretty safe. I know there have been issues with them catching fire, but that's largely been solved. However, if you look at what you need when the storage requirement is stationary, you can look to use other technologies that have problems that make them unsuitable for use in vehicles. For example, the sodium sulfur battery is well proven, it's well used in many countries, particularly in China, but it has the disadvantage it runs at several hundred degrees C, so you wouldn't want to put that in a mobile application, such as a vehicle or a van. However, if it were to store the energy and act as a buffer in a service station, you could easily install this in a building or an underground bunker. Another technology is the liquid metal battery technology. Now, one of the things with this technology is, again, it runs at high temperature, but if you look at the problem that you have with a lithium-ion battery, it is limited in its use by the number of charge-discharge cycles, and that's because of degradation that occurs at the cathode and anode. Now, this can be decreased if you're constantly renewing the cathode and the anode, and this can be done by using liquid metal. It could be sodium or it could be other materials. And for example, in the Ambri battery, because you're constantly renewing the cathode and the anode, you don't have this limitation on the number of charge-discharge cycles. And if I recall correctly, they guarantee their battery continuous operation for 30 years. So that makes a big difference if you're now looking at how you might store energy in a stationary application. Now, there are other types of energy storage, and you can investigate these yourself. One, of course, is the use of flywheels, and there's a storage facility in New York that's been operating for over 10 years now, and that's a well-proven technology. So in preparation for this project, I would suggest you look at the following. The first is that you make sure you know how to chair a meeting and take proper formal minutes, not notes. And the reason for asking you to take proper formal minutes is because the minutes are in many projects a legal requirement, so the organisation that's funding the contract can see the progress of the project, and if there's any dispute during the course of the project, it can be seen exactly what was done, who was present at meetings and who was not, who agreed to take on certain actions and by when, and also what happens at the end of each meeting is that the chairman will sign the minutes the following meeting to show that all people present agreed with the minutes that were taken. The next point is, when you look for information, do check out sources in the university library and don't just rely on online resources. I also recommend that you read the technology sections of quality newspapers such as the Times and the Telegraph, and that you look at the house journals of professional organisations. For example, the Institute of Electrical and Electronic Engineers, their house journal is IEEE Spectrum, the Institution of Engineering and Technology, where their house journal is Engineering and Technology, and the Institute of Physics, where theirs is Physics World. There are others. So that's a brief introduction to this project, and I look forward to meeting all of you who have selected this particular project this year. Thank you very much.